Think about it. You do it dozens of times a day without even a second thought, plugging something into a wall socket. But have you ever actually stopped to wonder what's really going on in that moment? What kind of science is unleashed with that simple little click? Well, today we're going to follow that current and find out exactly what happens. So there you go. You plug in your phone, your laptop, your toaster. What did you just do? Well, you've kicked off this incredible chain reaction that involves raw power, a little bit of heat, some mind-bending invisible forces, and even a dash of chemistry. So let's start with the part you can actually feel.
Okay, so the first thing you probably think about with electricity is what it does. It powers our stuff. Simple enough. But the second thing you've definitely noticed is that it often creates heat. And it turns out those two things, power and heat, are totally, fundamentally connected by one single elegant law of physics.
And that law is called Joule's law. It looks like a fancy formula, but it tells us exactly why things get warm. It's actually pretty straightforward. The heat you get from a wire really just boils down to three things: how much electric current is flowing through it, how much resistance that wire has, and of course, how long you leave it on. The more current or the more resistance, the more heat you're going to get. It's that simple.
You know that warmth you feel from your laptop's power brick or your phone charger after it's been plugged in for a while? That's not a flaw, that's physics. It's literally Joule's law happening right there in your hands. It's the direct conversion of electrical energy into good old-fashioned heat.
And this brings up something that trips a lot of people up. We talk about having a powerful charger, right? But then our electric bill charges us for the energy we used. We tend to throw those words around, power and energy, like they're the same thing. But in the world of physics, nope, they are very, very different. So, what's the real story?
Okay, so let's break this down. Think of power as speed. It's measured in watts, and it tells you how fast you're using energy. Energy, on the other hand, is the total amount of work you've done. It's like the total distance you've traveled. So that 100-watt light bulb in your lamp has a certain power level, but the actual energy it consumes totally depends on how many hours you leave it on.
Now, of course, in the real world, measuring power isn't always that simple, especially when you're dealing with big, complex industrial systems. So engineers have to get clever. For some tricky circuits, they use this really cool technique called the 2-watt meter method.
And you know, the beautiful part about this method is just how simple it is. You take the two readings from the meters, add them together, and voila, you've got your total power. It's a really elegant solution to a complicated problem. All right, so that's the stuff we can feel. But what about the forces we can't see? All right, so we've talked about the heat. Now let's dive a little deeper into the invisible forces that are really running the show here. Because at its very core, electricity is all about one fundamental force of nature, electromagnetism. And it all kicks off with something called Coulomb's law. This is like the absolute ground rule of electricity. Opposite charges attract each other, and similar charges push each other away. This law also tells us that the farther apart those charges get, the weaker that force becomes. Seriously, every single electrical thing that happens is built on this one idea. And this is where it gets really cool. When electric charges are on the move, they don't just create electric fields, they also create magnetic fields. Electricity and magnetism are basically two sides of the exact same coin. And that magnetic field interacts with everything around it. But not all materials react in the same way.
In fact, based on how they react to a magnet, we can basically sort materials into three main groups. You've got your ferromagnetic materials, like iron, which are super strongly attracted to magnets. Then there are paramagnetic materials, which are just kind of weakly attracted. But then you have the real oddballs, the diamagnetic materials.
No, you heard that right. They're actually pushed away by a magnetic field. It's a really weak effect, but it's totally there. Things like water and even carbon are diamagnetic. They basically create their own tiny magnetic field that opposes the one they're in, which shoves them away. So, the big takeaway here is that magnetism isn't just about pulling things together, sometimes it's about pushing them apart. And this idea of magnetic influence, that's the magic behind how things like transformers work. The concept is called mutual inductance. If you put two coils of wire near each other, the magnetic field from one can actually create an electric current in the other, all without them ever touching. It's amazing. And in a perfect world, that relationship is as simple as this formula.
All right, we've gone through the physics of heat and these amazing invisible forces. But now for the final piece of the puzzle. How do we store all this energy so we can take it with us? Well, for that, we have to jump into a whole different field of science, chemistry. Let's talk about batteries.
And the key to all of this comes from a scientist named Faraday and his law of electrolysis. What he discovered was incredible.
There's a direct, totally predictable link between the amount of electricity you pass through something and the amount of chemical change you can create. Simply put, more electricity means more chemical reaction.
And that is the fundamental reason batteries work. A battery isn't some magic box. It's just a clever device that uses a chemical reaction that can go both ways. When you charge it, you're using electricity to push a chemical reaction in one direction. And when you use the battery, that reaction just runs in reverse, releasing all that stored electrical energy.
And this is exactly why we have two main kinds of batteries. The primary ones, you can think of them as first-generation batteries, are your single-use disposables. Their chemical reaction only goes one way. But the secondary, or second-generation batteries, are the ones we all know and love. They're rechargeable, because that chemical reaction can be reversed over and over again.
And you see this tech absolutely everywhere, from the huge lead-acid battery in your car to the tiny lithium-ion batteries that power our phones and laptops. This also includes older, but super important, batteries like nickel-cadmium, which were the workhorses for everything from early cordless phones to electric cars for years.
So let's bring this all the way back around. The next time you plug something in, remember what you're doing. You're completing a circuit. You're letting power flow, which creates heat because of Joule's law. That whole process is controlled by the invisible forces of electromagnetism. And if you're charging something, you're using Faraday's laws to turn that electricity into chemical potential. It's this beautiful symphony of physics and chemistry happening every day.
We've managed to harness these incredible fundamental laws to build our entire modern civilization. The discoveries of Joule, Coulomb, and Faraday are literally powering our lives at this very moment. And it makes you wonder, as we face huge challenges like energy storage and efficiency, what new discoveries are still out there, waiting for us? What's the next great electrical breakthrough that's going to define our future?